In late 1945, Alan Turing found himself designing a computer at the UK's National Physical Laboratory. It would have been one of the first ever built. It was called the ACE, the Automatic Computing Engine. He felt it was important to be able to break down large programs into small programs, large routines into subroutines. He also felt it was important to be able to reuse these subroutines, so that if you wrote a great square root subroutine, then you could reuse it in a different program rather than having it always tied to the same program you wrote it for. He wrote down a rather interesting, novel method for implementing this subroutine idea. When we wish to start on a subsidiary operation, that's a subroutine, we need only make note of where we left off in the major operation, so a note of where we came from, and then apply the first instruction to the subsidiary, so go into the subroutine. When the subsidiary is over, we look at the note and continue with the major operation, so we return back to the main routine. Each subsidiary operation can end with instructions for recovery of the note. How is this burying and disinterring of the note to be done? There are, of course, many ways. And one is to keep a list of these notes in one or more standard size delay lines, which is a kind of storage at the time, with the most recent last. The position of the most recent of these will be kept in fixed temporary storage, and the reference will be modified every time a subsidiary is started or finished. Let me show you what he's talking about here. So here we have a small program which prints out Hello World over 3 subroutines. It has 2 registers, TS1, which will function as the instruction pointer, pointing to the next instruction to execute, and TS31, which points to the next place we'll bury data into. We print out the first chunk. Then we execute the instruction bury, which, as Turing describes it, stores the content of TS1 with 1 added to the position indicated in TS31, and then adds 1 to the number in TS31. We then continue execution. The next instruction uses TS1 to jump to instruction 45. We print the next chunk and then perform the burying operation again to get to the third subroutine. The third subroutine prints out a chunk and then executes unbury. Unbury, as Turing puts it, indicates that the value of the address given in TS31 is taken to be the address of the next instruction. This takes us back to the instruction just after our previous go-to. He actually doesn't say that we should decrement TS31, but I'm going to add that in as my minor contribution to Turing's work. We then print the next chunk and unbury again to take us back to the first routine and finish the program. Turing is describing a simple call stack, but he uses the terms bury and unbury rather than the terms we're familiar with, like push and pop or call and return. He doesn't say why he calls them these slightly strange words, but I have an idea, and I should say actually his biographer had the same idea, which is that Turing was a bit of a fan of burying things. He actually, during the Second World War, he was worried that the Germans might invade and that he would lose all of his life savings. So he converted them into silver bars, silver sort of, like you'd see in a film, and he buried them in Bletchley Park, and then he made a note with some coded instructions on how to find it again based on the landmarks around that place, and he put that under a bridge. And then after the war, he came back and he found his note, but the landmarks had all changed over this time, and so he couldn't find his silver bars, and they're still there, like he never found them. And so I think all of this business about burying and unburying things and notes must have been on his mind. His design for the ACE computer was met by his colleagues with a certain amount of skepticism. They really felt it was overcomplicated and kind of unnecessarily elaborate for what they really needed. So they didn't really build it, and he got disillusioned and left. They stripped down his ideas after he left and removed the bury and unbury stuff, and then built something called the Pilot ACE, which took another 5 years to really be completed. But Turing wouldn't live to see the consequences of so much of his work. 6 years after he wrote that initial design for the ACE computer, he was prosecuted for homosexuality. As the Cold War ground on, Western governments saw gay men as subversive and a risk to security, and so Turing, a man who had spent the entire war with the full force of his intellect bent on supporting his country by cracking the Nazi communication codes, was barred from all government work. 2 years after his prosecution, he was dead, aged 41. What would our world be like if Turing, who was recognised as a genius in his time and in retrospect, had had a career longer than 15 years? It's impossible to say, but this idea of the stack was too useful to go unnoticed for very long. One place it pops up, or perhaps becomes disinterred, is in the work of the Australian Charles Hamblin in 1957. By this time, computers were commonplace enough for people to learn to hate programming. In fact, His paper on this starts really punctually with, I suppose everyone would agree that programming a modern digital computer is a laborious and sometimes extremely complicated task, but not everyone would agree what, if anything, is to be done about it. Some programmers seem to be just plain defeatist, to accept the situation as a consequence of the laws of nature. Unlike the elegant language of mathematics, computers required specifying everything in laborious detail. Not just the operations, but also the addresses of every single piece of data would have to be exactly correct, and people were messing this up all the time, and it was a huge issue. So in this area there was great interest in trying to find a way to automatically generate instructions out of more friendly languages. One example to start with is just simple arithmetical sums, like 34 plus 55. It would be useful to have the computer translate things like that into the instructions itself. One of the problems with doing this is that sums with infix notation and brackets, they're not tackled in a sequential order, and computers aren't going to be able to just see which part of the sum needs to be done first. Now, Hamblin started off, and indeed continued after his foray into computing, as a philosopher. So he was familiar with some of the philosophical problems of recent history, one of which was, how can you specify logic unambiguously? So he knew about the work of a philosopher called Jan Łukasiewicz, who had found a way to specify logical operations without using brackets and without any ambiguity by putting the operators first and the numerals second. Hamblin calls this in his paper the so-called Polish notation, which is how it's generally known today, but if you want to seem really cool, you can call it the Łukasiewiczian notation. Something like that. Hamblin proposed that this notation is better for computers if we put the numerals first and the operators second. Then you can process arithmetic using what he called a running accumulator, but we can call it a stack. And let's talk a little bit about that while we're here. This is a very simple visualization of the stack as an abstract data type. That is, we're not thinking about how we implement it, just the idea. The most essential operations are push and pop. Push adds an item to the top of the stack, and pop takes an item off the top. I did invest in using my pop shield for this video, so I hope it's helping. There are two other operations that the abstract data type of the stack typically has. It's isEmpty, which tells you if it's empty, and peek, which lets you look at the top one. So you might see those referred to as well. But the main ones we care about are push and pop. Hamblin put the stack, or the running accumulator, to work evaluating reverse Polish notation expressions like this. The algorithm is very simple. You work through the expression left to right. If you see a number, you add it to the stack. If you see an operation, in this case addition, you pop the top two items off the stack, perform the operation, and push the result back onto the stack. We can do this with multiplication, division, and subtraction, though the order for subtraction and division are worth paying attention to if you want to implement this yourself. Just like Jan Łukasiewicz's forward Polish notation, this reverse Polish notation doesn't require brackets. You can work through it totally sequentially, no jumping around, no nesting, no recursive structure at all. So it's very computer friendly. In modern programming, this is also sometimes called postfix notation, as opposed to prefix notation with the operators before or infix notation with the operators in the middle. It's also interesting to note that Hamblin's computer, the computer that he got access to at his university, was actually based on the Pilot ACE design, which is of course based on the ACE design that Turing wrote back in 1946. So there's a bit of an interesting connection there. He also proposed using what he called a nesting register, just another stack really, for storing return addresses. In fact, he called this the most crucial part of his proposal. And also, in an act of Fermat-like hubris, he wrote down a footnote. He said, "Should this reverse Polish symbol order prove for some reason comprehensible only to formal logicians, I have a final trump card in the shape of a translation program which will accept a mathematical notation which is almost completely orthodox." But he didn't publish it until 1962. And I imagine he may have regretted this because around the same time, two German computer scientists, Klaus Samelson and Friedrich L. Bauer, were working along similar lines. They described an algorithm for calculating infix notation arithmetic rather than the reverse Polish notation which Hamblin had talked about. Here's how it works. You work through the expression from left to right. When you see a number, you add it to the stack. The first time you see an operator, you add it to a different stack. So we've got two stacks, a number stack and an operator stack. Except they didn't call them stacks though, because that terminology wasn't around. They called them cellars, or in German, Kellers. So they referred to putting numbers into the number Keller or operators into the operations Keller. I find that kind of poetic imagery, the idea of cellars in programming. We see another number and then add it to the number cellar. Then we see a multiply operator. Here we have a few different rules to follow. Before we add it to the operator cellar, we're supposed to evaluate the operators already there until one of three rules apply. Either the operation cellar is empty, we see an open bracket, or the precedence of the operator at the top of the operator's cellar is lower than our current operator. In this reduced example, what this means is if we have either a multiply or divide, we should evaluate operators until we see either a bracket, a plus, or a minus, and then stop. In this case, our current position is a multiplication operation, and the top of the cellar is an addition, so we stop immediately. Then we add our current operator to the cellar, and then we hit an open bracket, which we add to the cellar. Another number again, so we add it to the cellar, and we have an addition operation. We consider evaluating operators, but since the top of the cellar is an open bracket, we don't, so we add this to the cellar. We add another number, and then we have a multiplication operator, but again, we don't evaluate anything because the top of the cellar has an addition, which is lower in precedence. Another number, and then we hit a close bracket. When we hit a close bracket, our job is to evaluate operators until we hit an open bracket and then remove the bracket. So we evaluate the multiplication just like we did with reverse Polish notation, putting the result into the cellar. Then we evaluate the addition, again putting the result back into the cellar. Finally, we hit the open bracket and remove it. Next, we hit an addition operator. Our rule is to evaluate operators until either the operator cellar is empty, or it has an open bracket, or a lower precedence operator at the top. There is no lower precedence operator than addition in this system, so we evaluate all the operators, pushing the result onto the stack. We then add our addition operator to the operator cellar. Then we press on, adding another number, then a multiplication, then a division. Hitting the division operator means that we evaluate the multiplication, since we're supposed to evaluate until we hit a lower precedence operator and multiplication is the same precedence. But we don't evaluate the addition since it is lower in precedence. We hit a 4. Add that and then a subtraction, which drives us to evaluate the division and then the pending addition. Finally, we hit the end of the expression, at which point we must evaluate the remaining operators. That's the subtraction. This yields our final result. This might feel like a lot of arcane rules for what feels to us like a simple operation, but if you pay close attention to the evaluation, you might notice the algorithm is reasonably intuitive and similar to what you'd do if you were doing this by hand. If you hit a close bracket, well, you've just finished reading a bracketed expression, and that will need to be evaluated before any other operation that might happen on it, so let's just evaluate that right now. Otherwise, you can break up an expression like this into chunks separated with additions or subtractions. So as far as multiplication and division is concerned, we can perform calculations as we go along, as long as we stop at a chunk boundary. But if we hit an addition or a subtraction, we can actually evaluate everything up to that point, as long as we don't go outside of the pair of brackets, and since we're looking backwards, we only need to check for opening brackets. The cellar or stack allows us to work through a recursive structure, like arithmetical expressions. In the paper I sourced all this from, Hans Langmack makes the argument that at the time, it was not at all obvious that it was even possible, let alone how to do it. Other contemporary languages like Fortran had systems to reintroduce clarifying brackets to help the computer understand what was required. Even today, to me, it feels counterintuitive that a fairly linear-seeming, greedy algorithm is able to process nested structure like this, but here it is. These ideas were actually all over the place at the time. There was another guy, a German called Kammerer, who came up with the same thing, or essentially a similar idea, but he had more flowery language about it, and let me quote you a bit of it. He says of what we would call a stack and what Samelson and Bauer called a cellar, most of these memory cells are in the subconscious of the automaton. And the paper I found this in has this nice line, how Kammerer came up with this psychoanalytic terminology could not be clarified. So, funny stuff. Samelson and Bauer thought this was a big deal. They actually even submitted a patent for it. It might seem kind of trivial to us now, but at the time, programming, as Hamblin had mentioned, was laborious and error-prone, and also in Europe, where there were several computers around, each computer was using a slightly different instruction set, and this was causing a lot of rework in the different institutions. Samelson's view was that computing was repeating the history of mathematics, going from simpler operations to more complex and sophisticated ones, and by getting computers to process mathematical notation, you could shortcut all of that process. They might have seen computers processing mathematical expressions as we see LLMs processing human language today. And it all hinged on effective evaluation of expressions, which they just invented a pretty neat algorithm for doing. So they were feeling pretty good about their research. But their algorithm isn't particularly well known today, and when it is referenced, it's commonly referenced under a different name. But to tell you about that, I'm going to need to tell you about recursion. In late 1959, Samelson and Bauer published their new algorithm along with quite a lot more under the name Sequentielle Formelübersetzung, or sequential formula translation. This was pretty good timing because they were also on the committee of a new programming language called Algol, which promised to solve a lot of problems, and they could use their new algorithm there. One of the controversial topics was recursion. Should a subroutine be allowed to call itself, or should that be ruled out by the rules of the language? There were a few problems with recursion. One of the biggest was that at the time, each subroutine would be given its own static area of memory called its activation record, and this memory would be allocated at the start of the program and not moved around thereafter. This activation record would store the local variables, the arguments, and also, crucially, the return address, so that the subroutine would know where to tell the processor to go back to once it had done. This is in many ways a pretty simple scheme, but it does have the consequence that a subroutine cannot call itself. If a subroutine did call itself, then when the outer subroutine called the inner subroutine, it would need to overwrite the space where its own return address was being stored. So the inner subroutine could return back to the outer subroutine, but the outer subroutine would have forgotten where to go back to. As a result of this, most of the committee were against recursion, including Samelson and Bauer. They felt it should be forbidden by the rules of the language. Even John McCarthy, the American computer scientist who invented Lisp, and who was pretty keen on recursion, felt that recursive subroutines were inefficient and so should need to be marked specifically as recursive, while all the other subroutines would not have that functionality. And even that was voted down by the committee. Recursion was, in the committee's view, kind of an imaginary idea. Computers weren't actually able to recurse. They executed things in sequence. So why wouldn't you just write the code according to how it would really execute, rather than trying to pretend that it could do recursion? To them, it didn't make any sense. It just seemed fanciful. And it was pretty big beef at the time. There was actually a conference that I read about where somebody was giving a talk on recursion, and somebody put their hand up and made a comment that they were here really to work with Algol, not to play with it, and they hoped that we wouldn't become some sort of Algol playboys. So cutting stuff. There was one person, though, who did want recursion in Algol. He wasn't on the committee, though, so he couldn't make his feelings known directly. Instead, a month after the committee had concluded and finalized the design of the language, he phoned up the chair, Peter Nauer, and he dictated a small suggestion to clarify some finer points of the way the language worked. It read like this: any other occurrence of the procedure identifier within the procedure body denotes activation of the procedure. Peter Nauer was struck by the beauty of this phrase, and so he put it in, and when the report was circulated for final checks, nobody noticed it or its implications, and so recursion was in the language. This sentence implied a complete transformation in the way the language had to work, a transformation that would have to take place even though most of the committee had already been working on their compilers and interpreters for years by that point. A sentence which nobody really knew how to implement. A sentence written by a 30-year-old Edsger Dijkstra. I'm kind of assuming you know who Edsger Dijkstra is. If you don't, a great time to learn about him. In many ways, he was the world's first serious programmer, in that, not in a literal sense, people have been writing programs for a long time before that, but he was the first person to be really interested in programming languages and making the languages good and elegant and expressive, as opposed to just representing what the machine needed to do in an efficient way or treating them as mathematical objects. So he's kind of a big deal. And 3 months after inserting this sentence, Edsger Dijkstra publishes a now very famous paper called Recursive Programming. In it, in just 7 pages, he lays out an execution paradigm which is still the fundamental basis of how programs execute to this day. He cites only one reference: F. L. Bauer and K. Samelson, Sequentielle Formelübersetzung, sequential formula translation. He glosses over their work in the first page before saying, "The above is well known and so elegant that we could not refrain from trying to extend this technique by consistent application of its principles." And this he does. deftly simplifying and extending Bauer and Samelson's work into what we would now call a calling convention, a way that main and subroutines can manage their local variables, arguments, return addresses, and return values. I'll show you a simplified version of how it works. Dijkstra's argument starts with reverse Polish notation as we know it. Here we have a simple expression, 5 plus 18. This happens in 3 steps. Add 5 to the stack, add 18 to the stack, perform addition, and you get 23. Dijkstra makes the point that as long as the stack ends up in the state of having 5 and then 18, then the step which adds 18 could be anything. It could, for example, be a subroutine call which evaluates to 18. So how could we do this? To explain that, let's look at a program I've written in a kind of pseudo-assembly. And I do say that seriously. These are imaginary programs which work broadly like Dijkstra described. It's almost certainly not precisely how your programs work today or exactly what Dijkstra described in his paper, just an approximation of the broad idea. This is a routine whose job it is to evaluate reverse Polish notation expressions. You can see ours in the top right. At this point in the program, the state of our stack is 5 and 9. Let's assume we have some code elsewhere which will pass the expression, add numbers to the stack, and perform addition. But in our operation, we now have an operation double, which we're going to use a subroutine to perform. Double pulls one item from the stack and then returns that item doubled. So our evaluation routine has to call double, give it some arguments, a return address, and possibly some other things. This is how it does it. First, it pushes the parameter to double onto the stack. In this pseudo-assembly, it does this by reading the stack pointer 103, subtracting 1 to make 102, reading that memory address from the stack and then pushing the result on. In reality, this would take more instructions, but you get the idea. Then we push a 0 to the stack, which is going to be a holding spot for our subroutine's return value. Then we push a return address, similar to how Turing described earlier. This ends up being the address of the instruction we want to resume at, 38. Finally, we use a goTo instruction to transfer control over to our subroutine. That subroutine now has the responsibility to return everything in a good state. Let's assume it does so and we end up on line 38. We now have to remove from the stack everything that we added. We pop the return address, and when our function executed, it put a value inside the slot for our return value, so we pop that return value and save it to a register. Then we pop the parameter we passed to the subroutine and the original argument that double took, similar to how the addition operation will pop and remove 2 items from the stack and then add 1. Finally, we push our return value back on. And now note that our stack is exactly where it would have been without a subroutine in our previous example. This is promising. The stack and the rest of the operations have no idea this subroutine has taken place, just as long as the stack ends up in its right state. So how does the subroutine side work? Let's take a look at it. Within the subroutine, the first thing we do is set up a frame pointer. We do this by setting the register fp to the same value as our stack pointer, which is sp. What this means is that we now have a static pointer into the stack, which isn't going to change if we push new items onto the stack. As a result, we can now reference the return address, the spot for the return value, and the parameter by subtracting 1, 2, and 3 from the frame pointer. We can also push a new value to the stack. Let's call this one factor. It's equivalent to a local variable. We could probably do without it, but I just wanted to show you local variables. If we needed 3 local variables to compute our subroutine, we could push 3 slots onto the stack and then reference them as fp plus 1, 2, or 3. In this way, our function has its own environment in the stack which stores its state. This is called a stack frame, and fp stands for frame pointer. You might be thinking, well, you could just use the stack pointer and keep track of how it had changed as you added new things to the stack. And that's true and useful for compilers, but pretty annoying for us, so let's keep track of a frame pointer with fp. We then load some items from the stack into registers to perform our multiplication. We do so and then store the result back into the slot on our stack. What's wrong with this? Think about this for a moment. I'm curious to see if you figure it out. Now, if you said, this isn't a stack anymore, then you're right. We're not popping and pushing values anymore, we're changing them inside the stack. This breaks the stack as an abstract data type, but of course our computer can cope with it just fine. This is one of Dijkstra's insights in his paper. If we use the stack but also break some of the traditional rules just a little bit, we get this much more powerful structure that we can use. Dijkstra has also innovated in making the stack store different kinds of data at once. That's one of my favorite things about the stack. It's a naturally heterogeneous structure. You can use it to store all kinds of different stuff because you as the programmer take responsibility for pushing and popping them in the right way. We finish our subroutine by resetting the stack pointer back to the frame pointer, which is the same as popping off everything we added to the stack since our subroutine started. This is another thing that's cool about the stack. It's really just one value, an address, with some extra rules around how we handle it. Finally, we pull the return address out of the stack and go to that address. This transfers control back to our caller. And recall Dijkstra's point about how it doesn't matter what happens in between stack states as long as the stack gets back into the right state when you expect it to. It's the same idea here. From the perspective of our main routine, the stack is now exactly where we left it with just one change. Our return value is now populated. As long as we respect the calling convention, which is the set of rules we have for calling and returning from subroutines, functions are now totally interchangeable and what we might call modular. We can abstract away what they do and just rely on the result. You can imagine adding other things to this calling convention. Dijkstra says it would be a good idea to store the state of the registers in the stack before calling the subroutine so that they can be restored afterwards, and a few other things. The exact details don't matter so much as long as you understand the idea of using the stack to store state, which can then be restored afterwards. Dijkstra explains all this assuming the idea that we're talking about a main routine A calling a subroutine B. But then in the final paragraph of this section, he drops what he's been wanting to say all along. In this process, nothing, and he italicizes nothing forbids A from being identical with B. The subroutine only has to appear in memory once, but then may have more than one simultaneous incarnation from a dynamic point of view. The innermost activation causes the same piece of text, by which he means code, to work in a higher part of the stack. Thus, the subroutine has developed into a defining element which can be used completely recursively. Let's see that in practice. In this case, we have a subroutine factorial and we've given it the argument 3. It's going to calculate factorial, which is the number multiplied by each number below it until 1. So 3 times 2 times 1 equaling 6. Factorial is a naturally recursive operation because factorial 5 is 5 times factorial 4, which is 4 times factorial 3, etc. We go through the initial function setup, we check whether we're at the base case, which is 1, and since we're not, we go through the motions to call this subroutine again, but with a number 1 lower than what we got. This time I've made one addition to the previous example, which is that we save the frame pointer to the stack for restoring afterwards, and you'll see why we do that as we go on. When we get to call our subroutine again, execution jumps back up to the first line, and we go through the same lines of code again. At this point, we've built up 3 stack frames. You may notice how useful this structure is for debugging. We can see all the parameters and local variables of all the functions that we've called up until this point and where they're going to return to. This structure is still today the foundation of any good debugging practice. A stack trace is really just a visualization of the stack at that point in the program. It's also the source of the term Stack Overflow. You'll notice that with recursion, if we got the base case wrong, then our stack would grow forever until we hit some place of memory that it wasn't allowed to write to, or worse, it would start overwriting other things that it shouldn't. Systems today protect from this and trigger stack overflow errors when the stack has gotten too big, or in lower level languages, segmentation faults when the stack has grown to the point where it wants to write to segments of memory it isn't allowed to. But we don't want to recurse forever, so we have a base case, which is where factorial is 1, where we just want to return 1. In that case, we jump down to the end of the function. This end section stores the register T1, which is our result or our argument depending on the way our subroutine went, to the stack, resets the stack pointer and goes to the return address. This returns one layer down. Our caller function finishes deconstructing the stack frame, saving the return value and also restoring its own frame pointer so it can use that to calculate the right offsets. It then performs the multiplication, in this case 1 times 2, and returns it. This takes us back down another level and we do the same thing, storing our return value 6 to the stack, at which point I'll stop the program since I've not invented anything real to return back to. So it all works. Dijkstra has devised an elegant scheme for dynamically allocating activation records in stack frames, which fully supports recursion, along with lots of other things we might want. It doesn't require any fancy random memory allocation tricks, and it also fits in with the existing work of his valued colleagues. I find it hard not to be a little charmed by Dijkstra's antics in this story. He sneaks recursion into the language under everyone's noses, and then while everyone's arguing about how to do it, he says, listen, it's not that hard, it's your own research, and then he draws out of their research an implementation which is stark in its elegance. Or maybe he was just trying to be friendly. Either way, it's hard not to be charmed. To add insult to injury, Samelson and Bauer's infix expression evaluation algorithm is now better known under the name Dijkstra's 2-stack algorithm, even though he never claimed it, and as far as I can tell, it's just a mistake in some algorithms textbook from a few decades ago. He did publish an algorithm called the shunting yard algorithm, which is related but definitely different, so Yeah, this infix thing is totally not him. And Dijkstra, I believe, is also the first person to call them stacks, so I think he's the reason we call them that rather than cellars. There's also one other acknowledgement in Dijkstra's paper. It's to a man called Harry Huskey, an American, and it reads, "The author had the great privilege of having some inspiring conversations on the subject of this paper with Professor Huskey when he was the guest of the Mathematical Centre, Amsterdam, in the summer of 1959. And Huskey had published some of this stuff before. He described an idea called reversion storage, which stored in reverse order the addresses one must return to after the completion of the respective subroutines in order to proceed. And this also had an acknowledgement. This approach was developed at the National Physical Laboratory, England, in a group headed by Dr. A. M. Turing." So perhaps Turing's idea made it after all, or perhaps not. I actually read another comment by Dijkstra that he hated working with Huskey so much that it was one of the few times in his career that he had cause to bang his fist on the table. So perhaps they didn't talk that much about stacks. Still, it's a nice story. It's late. I finally, I think, almost got this video done, apart from this, which means it's time for me to say this video, like all Ode's videos, comes with a page on the Ode's website where you can look at the resources that I used to build this video, as well as some exercises, because all of this is to tempt you to get your hands dirty actually building some of this stuff and starting to build a more fundamental hands-on understanding of how computers work. Although, funnily enough, when I was researching this video, I read this paper. It was a kind of grumpy paper by Dijkstra many years after the events of this video, and he made he made a very interesting point, very compelling point, that when you're teaching computer science, I think it's called "On the Cruelty of Really Teaching Computer Science," and his point was, programmers should not be thinking about how the computer operates. They should be thinking about how algorithms work, and just forgetting about this kind of operational model, and instead thinking about, I don't know, the fundamentals of computation, and getting tied up with the machine gets you like muddled around in all the details and stops you from really making the big breakthroughs, which was sort of interesting to me because it wasn't what I expected to hear from him. But having read a bit more about his work now, a lot of his big advances in his career came from actually not being a hardware guy. So he was one of the, when he started working, everyone was thinking about hardware and he was thinking about software, about how programming languages should work. And he would have he put together a document with his team, which would be like, this is how the programming language should work. You go and build the hardware to interface with this, and I'll worry about the software, and then it should work on the computer when we're done. And so his big trademark was not thinking about how things really work, but instead thinking about how the language should work. And so for him, software engineers focusing on how things really worked on the machine level was sort of, it was holding them back. So it really made me think that, as well as many other things in the course of this video. So you'll be able to tell by this point these epilogues are supposed to be a little more rambling and casual. So yeah, thanks for watching them. Anyway, exercises. We've got some exercises. If you're here at this point, wasting your time watching me ramble on, you definitely have time for some exercises. We've got two exercises, one for everyone and one also for my lovely members. The one for everyone is to build a reverse Polish notation evaluator, which is, I think, a bit of a rite of passage in computer science degrees. So it's worth doing anyway, worth having built one at some point in your journey. So I've made it extra fun by we're not just going to deal with small reverse Polish notation expressions. Instead, I've made a really, really long one, like really, really long. So you're going to benefit from having built your own so that you can evaluate this really long one and then send me the number, and then you'll know whether you got it right. For members, there's another exercise, similar spirit, but slightly different. So if you would like to support this channel and get little extra exercises and extra material with each video, then if you click on the link in the description, then there's a million links and buttons that will funnel you through to the right place. And of course, I really appreciate the people who decide to do that and enable me to make these videos and the stuff that goes with them. I am tired. I've also I went on a real journey with After Effects in this video. You may be able to tell through the animations. I started off not wanting to do After Effects. Then I learned some After. I was like, oh, this is really cool. And then I learned some After Effects, and I hate it now. I've been doing too many horrible things with After Effects, so there'll be either more or less of that. So we'll see. Anyway, I need to stop talking and then get this video out. I forgot one part. I read a lot for this video. I read books, papers, all kinds of stuff, internet resources, everything. I put a list of the main resources that I used on the Ode's website. You know what? I'm actually going to go through everything. Alan Turing's proposal for the ACE computer. I can see why everyone was massively confused by what he was talking about, way ahead of his time, but also just all the vocabulary is completely... I mean, I know what he's talking about because I'm living in that world now, but the vocabulary is hard to get through. So it's a tough read, but a fascinating one. I didn't read too much of Harry Huskey's semi-automatic instruction on the Zephyr, just enough to get the Turing bit. Charles Hamblin's An Addressless Coding Scheme Based on Mathematical Notation is super readable and actually great. It's also typeset really nicely in Ragged Right typewriter. So definitely recommend reading that if you want to understand that period of computing history better. And I think he was a bit cut off in Australia from the rest of the computing field, and the fact that he came up with all this stuff, probably not in isolation, but a bit cut off from the rest of the field, is super impressive. Not that he needs me. I mean, he's no longer with us, so he's not going to feel one way or the other about me praising him. But anyway, Samelson and Bauer's sequential formula translation. I did not get very far into their prose, but there was a great German volume, Keller, Stack und Automatisches. I usually practice the pronunciation of other... You get the idea. Basically, it's Celler, Stack, and automatic memory, a structure with potential. There's the first paper in that, if you can read German, which I can't, but I translated it, got it translated. The first paper in that is really good. Actually, the whole thing's really good. The stuff about camera is really fascinating, and how he thought the stack, he sort of described the stack as like the top of the stack being the conscious mind, and lower down in the stack being the unconscious mind of the machine. Fascinating. Would have loved. And also there was some... Apparently he was he was never really appreciated in his time because everyone else kind of got to everything before, or at least published before him, so nobody really discovered his work. And he was tasked with doing a sort of summary of the field some years later, and he didn't even mention his own work in it because it wasn't important, which is kind of sad, but I guess gracious. Edgar Dijkstra's recursive program, we've talked loads about it today, but you should absolutely read it. It's fascinating. And unusually for him, very readable. Sometimes his stuff in English is not super readable, but I found it really readable. Alan Turing, The Enigma, which is Andrew Hodges' biography of Turing. Great. If you want to understand a bit more about how Turing lived, then a really fascinating book. Particularly the end of his life really enlightened me actually about what might have been going on in his head then, plus just a fascinating story about a fascinating person. So give Andrew Hodges' book and website a read as well. I actually haven't looked up how to pronounce Don Knuth. It's probably just Donald Knuth. Articulated programming, you can't go wrong really. A brief history. This is great. A brief history of the stack by Sten Henriksen. Just brilliant. Ends with like a comparison of the stack to like sort of old folk tales where the woman like swallows the fly to catch the spider. All that sort of stuff. Just wild. Really great paper. Dijkstra's Rallying Cry for Generalization, The Advent of the Recursive Procedure by Edgar G. Daylight. First, great name. Second, great paper. Really, really interesting. It's where all the stuff about Dijkstra banging his hand on the table came from, and a real insight into what was going on in the field and why people were for and against recursion at that time. I didn't include it in this video, but one of the things that came out of Dijkstra's sort of campaign for recursion was, Quicksort didn't really come out of it, but Quicksort was much more elegantly expressed in recursion. I think Dijkstra felt very excited about that, and I think that comes up in that paper as well. And that's it. That's my brief rundown of the things that I really enjoyed reading in the course of this video. Okay, now we're really going to end it because I've got to post this and I've got to go to bed. Good night, or have a good day.